Today we are starting operational amplifier. It is a design transistor that is make for operation plus amplification. Operation, it can perform many mathematical operation like addition, subtraction, multiplication, differentiation and integration. It can also amplify the input signal that is provided on its inputs. The general diagram of op-amp is like this. This is non-inverting terminal, this is inverting terminal, this is the output, this is plus VCC, and down here is minus VCC. There is V1 and there is V2. The V output is equal to A naught, which is gain, and VD, which is difference between these two voltages. So V output we can write as A naught V1 minus V2. So this is our output voltage. So larger the difference between these non-inverting and inverting terminal, the largest the output voltage. So it amplifies the difference between the input voltages. And this A node is gain. And the graph of A node with the frequency is like this. As the frequency of a signal increases, the gain decreases. The positive terminal is non-inverting terminal. The negative is inverting. And why are these name of this terminal? That will be made clear later. So we have learned the gain, which is A node. This is open loop gain. When there is no connection between the inputs and output terminals, then this is called the open circuit, open loop. The gain in this open loop is A node, which is open loop gain. Then we have some properties of op-amp. The first property is that input impedance is infinite. There is input impedance that is going to be infinite. So input impedance is infinite, so it can't change the signal which it tries to measure. The second is output impedance is equal to 0. Output impedance is equal to 0, so it can drive any device without losing its clarity of its signal. The third is voltage gain is infinite. So A naught is approximately infinite. The fourth property is V output, which is equal to 0 if V1 which is equal to V2. This is an ideal op-amp. Then the fifth property is bandwidth, which is equal to infinite. Bandwidth is of what frequency the op-amp signal amplify. If bandwidth is infinite, then it can amplify all frequency of signal. Then there is sixth property. Sixth property is infinite CMMR, common mode rejection ratio is infinite. And seventh property is slew rate is infinite. And the eighth property is output offset voltage, which is approximately equal to 0. Now we have to see the characteristic of op amp. Characteristic is look like this. This is V output. This is VD, difference between the input voltage. So as the difference start is increasing, the V output start increasing. As the difference start decreasing, the V output start decreasing. Then at a certain voltage, it will stop. And these were plus VCC and these were minus VCC. Plus VCC minus VCC. And the slope is V output, which is A node VD. This is graph between V node and VD. The slope is A node. The slope is A node. So when it start increasing, this is the saturation voltage. Plus V saturation. This is minus V saturation. The op amp has these two terminals and this is output terminal. This is input terminal. But it has these two terminal also, minus VCC and plus VCC. These are saturation voltages. These and this. It has two configuration. The first one is open loop and second one is closed loop. Open loop is there is no connection between input and output. Closed loop there is a connection between input and output. First we have to study the open loop configuration, then we going to study the closed loop configuration. In open loop it is act as a comparator. It compares the voltage between the input terminals. At the input terminals. This has many disadvantages. So we don't use open loop very often. We use closed loop for most operations, but we may use open loop for many things, but it has many disadvantages. With its gain is very high. The second thing is bandwidth very small, so it can only amplify the small range of frequencies. The third is smaller signal amplified. Small signal, the bandwidth is small signal amplified. Small signal may be amplified, so it can amplify also noise. Noise will also be amplified, which is a disadvantage of this. We don't want noise in our signal, output signal. There is also distortion in signal. These are its disadvantages. So V output, we already know the V output, which is equal to A node VD, which is equal to A node V1 minus V2. V1 minus V2. If V1 is greater than V2, then V output, which is equal to, if V1 is greater than V2, then V output is plus V saturation. This is that, this saturation plus negative, plus V saturation minus V saturation. So gain is very high. This is approximately infinite. Whenever the difference is positive, it is multiplied by infinite and then it hits the plus V saturation voltage. Because V output cannot be infinite, it's capped at plus V saturation. When V2 is less than V1, then V output is equal to minus V saturation. So now we have to look at some of its examples. V1 which is equal to sine omega t and V2 which is equal to 0. And V saturation is plus minus 15 volt. Then what is the V output? So it is something like this, plus negative V output. This negative terminal at 0, so it is at ground. V output V1 is equal to sine omega t. This is plus 15 volt, this is minus 15 volt. Then what is the V output look like? So we have to first write the input and output signals. Sine omega t, this is sine signal. This gonna add, okay, this is equal to v output time. This is v1, this is v2. v1 is sine, v2 is this. So when v1 is greater than v2, this part, then the output is plus v saturation. So it is at plus 15 volt. This is minus 15 volt when it is positive. Then when v2 is greater than v1, this is in that region, this region, this is greater than this negative region, then the output is minus v saturation. So it jumps from this to this, then it repeats itself like this. So output is a square wave. Now we have to study the open loop inverting comparator. So inverting comparator, the input signal is on inverting terminal. This is inverting, this is non-inverting, this is output. So input signal is on inverting terminal, and plus v is at some v reference, and this is also ground. This is v reference, this is v something, v input. And what is this output is will look like? The v output, which is equal to a node v1 minus v2. So which is equal to a node v1 is v reference minus v2 is v input. This is our output voltage. So suppose we have a signal like this. This is v input and this is v reference. So the v output with time is when v reference is greater than v input in this region. V reference is greater than v input, then v output which is equal to plus v saturation. So this is plus v saturation, this is minus v saturation. So in this region plus v saturation, and when v reference is less than v input, then v output which is equal to minus v saturation. So this graph will be look like something like that. So this is called inverting comparator when the input signal is at inverting terminal. Now we also have the non-inverting comparator. In which the input signal is at non-inverting terminal. V reference, V input, V output which is equal to A node, V1 minus V2 which is equal to A node, V input minus V reference. This is non-inverting comparator. So when V input is greater than V reference, then V output which is equal to plus V saturation. This is plus V saturation, this is minus V saturation. So when V reference is greater than V input, then V output which is equal to minus V saturation. Now we have to look about the output offset voltage. Output offset voltage. So when both the inputs of the op amp are at 0, suppose ground, this is also ground, then what is the output? The V output which is equal to A node VD, the difference between two terminal which is equal to 0. So V node which is equal to 0. This is an ideal op amp. But in a non-ideal op amp, the V output does not equal to 0 even if the both the input terminals are at 0. RL 0. So this is offset from 0. This is called the output offset voltage, which is not 0 but offsetted from the 0 voltage. To make it 0, we have to apply some input. So this is an op amp. This is negative, positive, the output. We have to apply some negative, some voltage, and V this is equal to 0. This is V in. So then Vd, which is equal to V positive minus V in, which is minus V in Vd. So V output, which is equal to A node minus V in, and V in, which is equal to minus V node by A. So net output now is V output offset plus V output. If V output offset is suppose 2 millivolt, then we have to provide V input. We have to provide V input such that when V add is added to offset voltage, then net which is equal to 0. We have to make net 0. So by this method we can solve the output offset voltage. Common mode operation of op amp. So we have this op amp. There is negative, positive. This is V output. This is V1, V2, Vd, which is equal to V1 minus V2. So if V1 which is equal to V2, V output which is equal to 0. But V output is not equal to 0. This is an ideal. In non-ideal, V output does not equal to 0. So what is the V output? Then we have the VC which is common voltage, which is equal to V1 plus V2 divided by 2. This is common mode. So V output, which is AD into VD, difference in voltage, plus AC. This is open loop gain. This is a common mode gain into VC. VC is this common voltage. So if VD is equal to 0, then AC, then V output which is equal to AC VC. So AC is equal to V node by VC. V node by VC. This is ACM which is equal to VOCM common mode. VCM common mode, which can be written as VOCM divided by VCM, which is equal to V1 plus V2 divided by 2, which is equal to 2 VOCM divided by V1 plus V2. So this ACM is common mode gain. Because this is a common mode operation. So if V1 which is equal to minus V2, then V output which is equal to AD VD plus AC common mode VC. So AD VD V1 minus V2 plus AC VC V1 plus minus V2 by 2. This is equal to 0. So we have VD AD to V1 V output. So AD which is equal to V node by 2 V1. This is when it have the opposite polarity. We have known that the output of an op amp is depend upon two things, which is open loop gain and difference between voltage, which is open loop, and this is common mode gain and common mode voltage. Then we have the common mode rejection ratio. CMRR. So this determines how much the op amp rejects the common signal on the input. If common mode rejection ratio is high, then it can reject the common signal more. If common mode rejection ratio is low, it can reject common signal less. So which is equal to AD ACM. We have AD which is equal to V output by VD, and AC which is equal to V output divided by VCM. And we have found out common motor section ratio as 20 log 10 AD divided by ACM. If ACM approaches 0 and AD approaches infinity, then this is an ideal op amp. Then we have the slew rate. The slew rate is the rate of change of output voltage. So it can be written as SR, which is equal to delta V naught by delta T, which is equal to V by microsecond. If V output which is equal to A common closed loop V input, then SR slew rate which is equal to ACL dV in by dt. If output is changes with the time very rapidly, then the slew rate is high. If it does not change with the time rapidly, then its slew rate is low. So we are now learning about the closed loop configuration. In this there is a connection between input and output, and it can be done in two ways. First is negative feedback, and the second is positive feedback. Negative feedback is when feedback is provided on the negative terminal. Positive feedback is when feedback is provided on the positive terminal. Negative feedback make gain small. It can act as amplifier. It also increases bandwidth. The positive feedback makes gain large. It acts as a waveform generator. Triangular, common square wave. So we have closed loop. So in this is our amplifier. Then we have V input, and there we have the V output, and this is equal to our feedback beta, taking the output to the input. Beta is our feedback. Then if A is equal to 2 and beta is equal to 0.1, then if V in is and V output and gain, if V input is 10, V output is 20, then the beta is equal to 2. If V input is 8, V output is 16, then gain is 1.6. We know V output is equal to A naught V1 minus V2. If we apply the feedback at positive terminal, then V1 increases. And V naught is also increased. If feedback is at negative, then V2 increases, V naught decreases, so gain will decrease. Then we have the closed loop gain. So we have the positive feedback, and there is negative feedback. In positive feedback, V naught which is equal to A V input minus beta V naught, because the positive the feedback, negative feedback, positive negative, the feedback is given at the negative terminal. So V output, here is V input. Now we have to learn about the closed loop gain. We have two type of feedback: negative feedback, and then we have the positive feedback. In negative feedback, V output is equal to V in minus beta V naught. Positive feedback, V naught which is equal to A V in plus beta V naught. So we have positive negative V output. If V output is at the positive terminal, then it is a positive feedback. So there is a signal add feedback to the signal. So it is add But when it is at the negative terminal like this, then we have minus beta V naught. Then V output divided by V in, we have A over 1 plus beta I, which is equal to gain. Here V naught divided by V in, which is equal to A over 1 minus beta I, which is equal to gain. So in a negative feedback, if beta increases, then gain decreases. In positive feedback, if beta increases, then gain is also increased. Then we have the virtual ground. In this, two or more points are at same potential. At same potential, suppose we have this op amp, positive, negative. Suppose we have an op amp, negative, positive. If positive is ground and there is a negative feedback, then it is at 0, then this will also be 0, no matter what the input voltage is. This is applicable in only in negative feedback. This is due to gain is very high, so op amp become perfectionist. So we have the V output, which is equal to A 0 minus V input, V output, which is equal to A minus V in,